thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. Hess's law derives directly from the law of conservation of energy, as well as its expression in the first law of thermodynamics. Hess's law can be used to determine the overall energy required for a chemical reaction, especially when the reaction can be divided into several intermediate steps that are individually easier to characterize.
There are two ways we can use tabulated thermochemical data to calculate the delta H of any reactions. The first way requires that we manipulate thermochemical equations in specific ways. So let them be aware of some rules. First, if the reaction has delta H, the reverse of the reaction have the opposite delta H, or the same number with reverse sign. Second, if molar quantities in equation are multiplied by coefficient, so is the delta H. So if you double all the substances, double the delta H.
These are the things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know the change in enthalpy associated with a reaction like this one, but it is difficult to measure scientifically. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want.
We can take other reactions with known enthalpy changes to align with our equation, like this both. And now here we have carbon graphite on the left where we want it to be. But our equation calls out for 2 moles, so we must double this. Next is we have CO on the right where we want them and at the right amount. So all we have to do is to add both equations together. So here are both equations, so we must add them together. And then we cancel these out because they're present on both sides of the equation. And now, after adding both equations together, we are left with substances the same as our original equation. And then we just have to add the delta H.
This kind of manipulation is allowed by Hess's law. We can manipulate coefficient of a reaction or reverse its direction as long as we change the delta H associated within the appropriate way. We can either add or subtract the equations as necessary to give us precise equations. The delta H you get by doing the arithmetic will be the delta H for the reaction.
So now, we will determine the enthalpy change of C2H4 plus 3O2 that gives the product of 2CO2 plus 2H2O. We can determine that using these reactions. So first, we will start by writing the chemical reactions that put the correct number of moles of the correct substance on the proper side. For example, our desired reaction has C2H4 as a reactant, and only one reaction from our data has C2H4. However, it has C2H4 as a product. To make it a reactant, we need to reverse the reaction, changing the sign of the enthalpy, which equals to, wow, okay, that's so wrong, which equate is C2H4 is equals to C2H2 plus H2, and change the sign from negative. Since we reversed it and we'll have to change the sign, it will be positive. So positive 174.5 kilojoules. There you go. Next, we need CO2 and H2O as a product. The second reaction has them on the proper side, so let us include one of those reactions. Then we write the enthalpy. Since we didn't reverse it, the sign of the enthalpy stays the same. Next, we note that we now have 4 moles of CO2 as a product. We need to get rid of 2 moles of CO2. The last reaction has 2 CO2 as the reactant. Let us use it as written. So now we will start canceling. So what cancels? First is 2C2H2. Next is H2. Next is 2O2. 2O2 and next one is this one. So this is why it looks cancelled. So now we will write down what is remaining. First, we write C2H4, which aligns with our reaction above. Next is O2. We need O2. So since we canceled 2O2 and 5O2, we still have 3O2 remaining. Next, we need 2CO2. So we have here 4CO2 cancelled by 2CO2. We still have 2CO2 remaining. And lastly, copy 2H2O. Now that we have the reaction that we are looking for, we have to find the delta H of this reaction. So to find that, we are going to add this reaction, which is equals to 1685.2 kilojoules. We found the change of our enthalpy.